minutes.
Okay.
You don't need to spend the 1.5 hours.
It goes faster.
So you can fast forward.
Yeah, you can fast forward on YouTube. So it's
like a movie.
Right.
It's like a movie. Good.
TikTok's too slow. You want to go faster, and that's great.
Alok, you can slowly start. I think very quickly people will join. It will climb up very fast.
Its population is increasing.
Very fast, yeah.
Okay. So is your YouTube channel is on?
Yeah, it is on. Yeah.
I have not read the message yet. Let me just check.
Yeah, sir, we are live. Yeah.
We are live. Okay. So good afternoon to everyone and welcome to this session. And also good morning to today's speaker, Professor Alex Magin. And it is our great opportunity to introduce, it's my great opportunity to introduce him. And I am happy to say that, to tell you that he was my postdoc boss in 2012. And I indeed have many sweet memories. It is our great pleasure to have Professor Magin with us today. And we thank him very much for accepting our invitation. Professor Magin is currently a senior professor at Laboratory of Theoretical and Physics and Mathematics, and I actually translated it from French to English. It's a CNRS unit in University of Cergy, Paris in France. He did his PhD from University of Paris in 2000, and he then moved to University College London as a postdoc. And then he came back to France in Grenoble in 2003 to join as a junior researcher, CNRS junior researcher. And then from there, in 2010, he moved to University of Cergy, Paris, and became a professor there. Professor Magin works in a diverse range of fields, and starting from quantum foundations, quantum scattering theory, semi-classical physics, relativistic quantum information, and many more. And he has made quite a number of important and interesting contributions to those fields. And it is our great opportunity here today to listen to him. And he will be talking about Wigner-Friend scenarios from the measurement problem to consistency of quantum mechanics. And with this, I would like to invite Alex to deliver his lecture.
Yes, so thank you very much for this very kind introduction. So of course, I'd like to start by thanking, Professor Pan and Professor Panigrahi for setting up this huge summer school, which lasts for over a month and followed by a lot of people. It's a lot of work. And I think it's really important because we have been kind of locked down or separated and just couldn't communicate it. It's really important, especially for the students, to be able to interact and have lectures and discuss. So again, thank you very much for setting up these huge series of lectures, and also of course for inviting me. I will try to share my screen. So
it started from.
Yeah, it started from here. So okay. Now it's fine. So I will talk to you about this Wigner-Friend scenarios, because there has been in the last 2 or 3 years a few works. I mean, not a huge increase of works, but trying to give a new perspective on this Wigner-Friend problem. So maybe I think Wigner-Friend is not as well known as Schrodinger's cat, and it's very similar. So it's a good opportunity to discuss this issue. And since this is a school, I think the starting point is related to the measurement problem. So I will talk a little bit about the measurement problem, and then I will introduce Wigners Friends. So in his original paper, so if you know the argument, I will just present the argument in a few minutes. Wigner said that consciousness is necessary to explain, to account for the measurement problem. And so I will briefly introduce Wigner's approach. Then I will give you basic rules of standard quantum mechanics. And I will take Feynman's approach, because it's really a pragmatic, just a set of rules without too much arguments behind that. And we will try to see how Feynman's approach accounts for this Wigner problem. And then, so I will briefly mention the recent works that have generalized the Wigner-Friend scenarios. And as you may know or not know, but basically these works tended to say that there is a problem with the consistency of quantum mechanics, or at least with the existence of objective facts. And so we will try to see what actually standard quantum mechanics has to say about this problem. Because of course, when we talk about measurements, it's a very ambiguous. Quantum theory is very ambiguous on how quantum measurements should be accounted for. And so maybe we are not always talking about exactly the same version of quantum mechanics. Then if I have time, I'll briefly show you how you can actually peek into the friends labs, because as you'll see, Wigners Friend, it's about a super observer observing a friend making a measurement. So I'll get to this in a minute. And we can actually peek into the friends lab with quick measurements. And then we'll conclude. So as I guess all of you know, we have a big problem with quantum theory is the about what problem. I mean, what is quantum theory about? So we know it's a theoretical tool that lets us compute probabilities, average values. But what is it talking about? How is it related to, physical reality? So this is a general problem. Quantum theory, we don't really know, right? What is it talking about? And then there's a specific problem, a special problem that is specific to measurements and how the theory accounts for measurements. So very briefly, so the about what problem, it's the combination of a very abstract formalism and the fact that we don't know what the theoretical terms refer to in physical reality. So the fact that the formalism is abstract, it's not a problem as such. If you just take classical mechanics, in the analytical mechanics, Hamilton-Jacobi formulation, you have this S function. It's called a classical action. It propagates in a multidimensional configuration space. It's like a shock wave propagating in some abstract space. And you have canonical transformations and so on. But it's not a problem because we know how to relate this to the motion of a point-like particle or of a solid made of a combination of point-like particles. And so we're safe from that point of view. We don't have this, right? So basically, how do we describe a system in quantum mechanics? Well, we have a vector in, Hilbert space or vector space more generally. And if we want to access the property of the system, well, there are things called observables. They are represented by operators in Hilbert space. And basically, we want to, so we need the spectral theory, and we have eigenvectors and eigenvalues of that operator. And this is basically how we should connect the eigenvalues to what we observe. And this is also the way we do a preparation of the system, where we prepare the system in the state and so on. But as Asher Paris famously observed, quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. This is his famous book, Quantum Theory, Concepts and Methods, that I recommend. And so we need a form of translation between what happens in Hilbert space and what occurs in laboratories. And the only thing we really lack the translation, except when we have probabilities and eigenvalues, and so that we relate to observables, right? And so that's the problem of the fact that we don't know what the theoretical terms, what the state vector relates to. So some people will tend to say, oh, it's pure information, but still it has to be related to what's happening, because information about what? That's always a question. Some people will tend to say, oh, it's real. I mean, reality is described perfectly by the state vector, but actually, of course, we don't know. So now let's get to the specific problem. So the specific problem, I think that most of you know this. Well, you have two kinds of evolution. You have the evolution of the first kind, which is a unitary deterministic evolution. That's Schrodinger's equation. And that's the way a system evolves when it is not measured, right? Now, when the system is measured, we have a second type of evolution. Something different happens. And so people are don't even agree on how this should be called. So it's a projection to eigenstates, collapse, wave packet reduction, irreversible active amplification, quantum jump. So you have different terminologies here. And the important point is, of course, that Schrödinger equation, the linear equation, is not valid anymore, and this is not a unitary process. Moreover, the theory is not really clear about when each rule should be applied. So there is some sort of split. Sometimes we use this first kind of evolution, then sometimes the other one. And actually, the way you split this is pretty much arbitrary and doesn't change your predictions, right? So a lot of names: Heisenberg cut, von Neumann chain, shifty splits. So this is these are the names that appear most often. And so Bell precisely, so this in this famous paper against measurement that was published just a few months before his death, his sudden death in 1990. Well, he kind of course, so he recognizes, as we all do, that for all practical purposes, this is the FAP terminology he coined, the quantum formalism works. I mean, we just apply the rules and we get the predictions that are perfectly verified. But still in this paper, he makes fun because he says, okay, I went to talk with famous physicists and asked them what is a measurement, and they replied to me, oh, you should go and look at what textbooks say. And then he makes fun in this paper because different textbooks give different accounts and not very clear accounts of what is a measurement. So there is a split, but a split is pretty much undefined. Is it quantum versus classical? Is it reversible versus irreversible? Is it macroscopic versus microscopic? Is there a rule for a conscious observer? He even makes fun of this. He says, I mean, did nature have to wait the appearance of an observer with a PhD in order to have observe a quantum jump? So this is so this is kind of the specific problem that appears when we want to account for measurements. So again, I just want to stress this, again, this is a school on two urban legends. So the first urban legend that would somehow say that, oh, well, it's a problem of interpretation because the standard interpretation has problems. But if we, there are many interpretations of quantum mechanics. So if we switch to another interpretation, the measurement problem disappears. So that's not correct. The measurement problem is always there. It's just that it appears in a different way if you interpret the theoretical terms in a specific way, like, Bohmian mechanics, many worlds interpretation, and so on. So the second point, second urban legend, somehow people say that decoherence would solve the measurement problem. So I think we don't hear this anymore nowadays. It used to be quite common maybe 20 years ago, 25 years ago. But I think now there's pretty much a consensus according to which decoherence cannot solve by definition the measurement problem. So even Zurek, who was one of the most vocal supporters of this position, now clearly says that, well, decoherence, what is decoherence? It's a mechanism that accounts for effective classicality by suspending the validity of the quantum principle of superposition. And so this is done in a statistical way. But overall, we still have entanglement for the superposition for the entire system. And so you cannot really solve the measurement problem. So a very simple illustration. So we have an incoming quantum particle here, for example, a neutron. We have a beam splitter that will kind of send part of the neutron here and part along this arm. And at this stage, between T0 and T1, we have a sum over what I call virtual paths. So there's bits of the state vector here, bits here. Now at T1, assume that we have a detector here, clicks. And so these virtual paths have become a single real path. Why? Because I'm assuming that the detector here did not destroy the particle, but just gave you there was a coupling that gave you a click. You can just measure again the particle afterwards, and you will always find it on this arm, and say called it 1. Now, of course, we can also wait up to time T1 and not detect the particle at E1. So there was no interaction, so to speak of, but still now that has become a real path on path 2. So you don't even have to wait for D2 to click. At this stage, you know for sure, so you could couple, again, other detectors and without destroying the particle. And so these two virtual paths would have become a single real path on which you always would always detect your neutron as long as you don't destroy it. So as you know, well, we could, at this time, so again, we have the particle incoming here, and we wait until the wave packets are on both arms. You have the virtual paths here. And at this time, we decide to close and to make an interferometer out of these two arms. And if we do this, as you know, so this is called that delayed choice, right? Because we close the particle, we close the interferometer once the particle is inside. And what we observe, as you know, is that the virtual path here will interfere. And so basically, it means that we do need to describe the system with virtual paths if we don't measure it. And as soon as we measure it, we have real paths. So Wheeler, who is the one who introduced this delayed choice setup, said that we cannot, it doesn't make sense to talk of the phenomenon until it has been brought to a close, well, by a measurement that he called an irreversible act of amplification. So this is very much what this Copenhagen interpretation says. It's language of the Copenhagen interpretation. So there's one more thing I want to tell you, which is the von Neumann model. So you know that von Neumann is the one who introduced these two kind of evolutions. Well, it was the opposite for him. The unitary one was called 2, and the projection was called 1, but never mind. So the von Neumann model tells you how your system, described by a Hamiltonian, is coupled to a pointer, described by this mass here, a free mass, by an interaction. So the interaction couples this observable of the system you're interested in, to P, which is the momentum of your pointer. So this is very much how you would describe a measurement in classical mechanics. And actually, if you look at the book by Paris I just mentioned, he just does the classical version of this. You know, Hamiltonian, Poisson brackets, Hamilton's equation of motion, and so on. So basically, you can do the same thing in quantum mechanics, and von Neumann was the first to have done this. So your initial state is the initial state of the system, psi, and a tensorial product with the initial state of the pointer. So if you apply Schrödinger's equation, what happens, because of this interaction, so of this coupling, your system and pointer will interact and actually get entangled. And at the end of this interaction, so I didn't mention that G was the coupling constant. So you turn it on and then it's very strong, and then you turn it off at some time. So it's time dependent. And so what I call here capital G is just the time integral of this little G coupling constant. But never mind the details. The important thing is what you get after you turned off the interaction. You get this entangled state, a superposition. So your pointer was initially at some position, and now it's you have the superposition of the pointer shifted by the coupling G times the eigenvalue, and this goes along with the system in the eigenstate corresponding to this eigenvalue, right? So you have a sum over all these things. It's a superposition. You don't have the single measurement that you will observe. So at this stage, you still have virtual paths. But this is all you can do with, of course, the Schrödinger equation in linear quantum mechanics. You cannot define a measurement outcome. You need the second step, the step you introduce for measurements. Good. So now let's get to Wigners Friends. So this was a paper published in 1961 or 1962. The starting point is this superposition I just discussed, right, between the pointer and the system in eigenstate AK, and pointer shifted by the corresponding eigenvalue, and all this is superposition. So there is a paper by London and Bauer in 1939 in which they say that the only way to kill the superposition is by introspection. So what they say, okay, so this is actually a snapshot of Wigner's paper, and I thought that Wigner had translated because this paper was published in French, and I just didn't realize it was also in French in his paper. So, well, never mind, because I don't know who said that English is a German spoken with French words, so you can probably understand. So what they say is that the observer here has a characteristic faculty that we can call the faculty of introspection. So it means that an observer knows his own state. And what London and Bauer said was that once the observer knows his own state, by introspection, this superposition doesn't exist anymore. So this is the starting point of Wigner's paper. And so, so the idea in this paper is that you have, so the super observer, the Wigner, well, for now it's just an observer, and imagine that you have an atom. So this would be, let's say, a sealed laboratory, and you have an atom going through a Stern-Gerlach, you know. So this is something you know as spin, if you want, that is going to be separated along on this basis. Well, how will W describe what is going on? Well, of course, he will just say, oh, well, I just have a superposition. Nothing is happening, and I describe this by a superposition. But now, on top of all this, let's assume that we have a friend here making a measurement. So we don't have just the atom going through Stern-Gerlach, but we have the atom going through Stern-Gerlach and measured a measurement coupling with a measurement apparatus here. So this is M is the state of the measurement apparatus, E, let's say, is the environment, and F is the friend, and she is making the measurement. So how should W describe this? Well, if we think that quantum mechanics is valid even for very complex systems, well, you would be tempted to say that we need to apply linear superposition, right? But if we apply linear superposition, Wigner tells us, well, does this mean that the friend would be like in some state of suspended animation until W actually asks her what she saw? No, of course, because of introspection. By introspection, F knows what she obtained. So this prompted Wigner to say that quantum mechanics needs a nonlinear modification. And he said that living beings have something special that modifies. So it's not, I mean, it's more than consciousness. He said that living beings should modify linear quantum mechanics because something is necessary. But still, even if for F, there is a nonlinear modification because by introspection, she knows the result. She doesn't see the superposition. She sees plus or minus. What happens from W's viewpoint? Because he didn't yet made this direct, he doesn't know what happened. His consciousness has not yet made the direct observation. There's no introspection. And so maybe W could still see a superposition, even though the friend obtained a definite outcome. So this is the question that Wigner raises in this 1962 paper. So of course, this was a paper published in a volume called The Scientist Speculates, an anthology of partly baked ideas. So again, it's really a very speculative idea, and Wigner will write again maybe 2 or 3 papers along these lines, and then he will change totally his mind later on. But if we take this idea seriously, then well, of course, we need to assume that linear quantum mechanics applies at any scale, as long as we are able to coherently control all the degrees of freedom. Then we have also to assume that the agent's knowledge, consciousness, changes her state vector, the state vector. So this would be some sort of implicit definition of measurements. Again, introspection, measurement is introspection. And this would change, at least locally, the state vector. Locally means for the agent making the measurement. But if this happens, if it's the state vector changes only for the agent making the measurement, then maybe this means that state vectors would become relative to agents, right? Because the friend would describe a quantum state in a certain way, and Wigner would describe the quantum state in a different way. And then, of course, if this is the case, then you see that measurements will disconnect the state vector from a single material world. And again, this is not a problem as such, in the sense that we don't really know what the state vector describes. So why not? You know, we can just, why not? Now, the question is whether this fits into standard quantum mechanics. So if you modify quantum mechanics by adding a nonlinear term, then the answer is, of course, no. But if somehow you think that there is, the introspection, agent's knowledge, and this doesn't do anything to your state vector, it just brings knowledge to the agent, as London and Bauer suggested, then it's worth having a look, right? So standard quantum mechanics is, how does the standard quantum mechanics account for measurements? So I will describe Feynman's pragmatic approach, because Feynman just gives a set of rules and doesn't start embarking on sort of aphorisms often associated with Copenhagen interpretation, like Bohr or Heisenberg about the limits of knowledge and so on. So it's like having Copenhagen. It's like having Copenhagen rules without all this romantic aspect of the Copenhagen interpretation. So it's very straightforward, pragmatic approach. So basically, Feynman is in his lectures. So probably all of you know this famous book, the Feynman Lectures on Physics, and there's also this second book, Quantum Mechanics and Path Integrals. But the first chapter deals with a summary of the rules of standard quantum mechanics. So this is it's actually given in a compact and very handy form in this Feynman and Hapes book. Sorry. So basically, Feynman tells us, if we want to compute probabilities, this is what quantum mechanics deals with, when we have to sum over the virtual path I showed you earlier, so those are called amplitudes, or when we have to sum over real paths, so probabilities. So once you make a measurement. And this, according to Feynman, depends on whether there is an experiment that records the path that is actually taken. So just to remind you, what Feynman calls amplitudes are these little things. So you have your system initial state as 0. It evolves. This is the unitary evolution operator from time t0 to t. And at time t, you find the system in state j. So this would be the amplitude as 0 to j, right? So I just gave you the simple example earlier. This is another very simple example given actually by Feynman. This is taken from his book, the double slit, right? So you have the electron gun, you have the two slits, S1, S2, and you have the detector, and you look at the detection pattern. So here, in this case, you have virtual paths, because you have to, as we saw in the simpler example earlier, which is actually quite equivalent to this one, we have a path going through the first slit here to the detector, a path going through the second slit to the detector, but we're not making any measurements. So what do? We sum over the amplitude. So the probability you obtain is the modular square of the two amplitudes. And as you know, we obtain this interference pattern, and this is what you learn in your standard quantum mechanics classes. Now, if somehow I I observe the slit through which a particle went, so I don't know, I can put a polarizer, anything I want that will not destroy the particle, but will tell me which slit it went through, then we don't have virtual paths anymore, because we made actually a measurement of the slit. So what do we have? Well, we have to sum over probabilities. We have real paths, and this is what you obtain here. No more interferences. It's probability of going through the first path, it's amplitude mod squared, and probability going through the second slit, or first slit, sorry, probability of going from R0, first slit, final position, and the one going through second slit. And so you just add the probabilities. So this is just the only thing you need to know. So we can collect Feynman's rules, so the rules of standard quantum mechanics in this very simple fashion. So he tells us again when we should add the amplitudes or add probabilities, depending on the records you have. And so, for example, if you look at rule F here, we see that the amplitudes are never added if information about the final state is in principle available, regardless of whether this information is known or used. So it's not a question of having an agent, being conscious of this, or an agent not being conscious of this. It's just that the information is there. There is a record. So the record can be the photons that get to your eye. It can be the sheet of paper with the printed outcome. It can be part of the observer's brain. But according to this view, quantum mechanics does not deal with the personal experience of the agents. We just have records. They're here or they're not here. If they're here, we add over probabilities. Otherwise, we have to sum over the amplitudes, right? So this is, let's say, a pragmatic view of standard quantum mechanics. So it's a pragmatic view and also a pessimistic view. You probably know these famous citations. Feynman thought that we can't really understand what is going on, right? So nature behaves this way, and you do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. So nobody knows how it can be like that. Or here again, we want to know, how does it work? What is the machinery behind the law? Again, no one has found any machinery behind the law. No one can explain anything more than the rules he gave. So it's a bit pessimistic, so it's grounded on this general idea, that humans are, smart animals, but still animals with some limited cognitive capacity, and so we can't understand everything. We have, science maybe can translate some mysteries into problems that it can solve, but we have cognitive limitations, right? We can't know anything, and of course we can also have a psychological reason saying, Feynman, it goes like something. Well, I'm Feynman, I'm so smart, I didn't understand a damn thing about this, so don't try, you won't either. Maybe that's also an explanation. Dirac, for example, was a little bit more optimistic. So again, he recognized there were these problems with measurement, with what quantum mechanics deals about, but he said, don't worry. We don't have to worry because we can actually use the theory and solve a lot of different problems. And when the theory will get to deal with the problems now, like the measurement and what the terms deal with, then experience will give us a hint. That means that we will reach a stage in which we will be able to make experiments in which we will get results that will allow us to understand what is going on. So maybe the Wigner-Friend is can give rise to such experiments. So Dirac also said that theoreticians can just forget about trying to guess what's going on. If they don't have input from experiment, no way it's going to work. So this is this is Dirac. So how would the Feynman rules account for a Wigner-Friend experiment? So again, we have this friend here. We have this qubit and Stern-Gerlach. The Friend's measurement apparatus, and here we have the record, right? The record, so let's say it's a printer. And again, we have now Wigner coupling his own apparatus and is going to measure the whole thing. What the rules tell us is that if we really measure the whole thing, so this is the initial state of the printer, of the memory, if you want. This is mu is for memory of the apparatus of the atom, this qubit you're going to measure. Then after the friend makes a measurement, it evolves into this plus part, all right? We have obtained plus here, it's coupled with apparatus in state plus, printer has printed plus, and we have a minus part here. So if Wigner couples everything, so we call this L, so L plus when it's plus and L minus when it's minus, if Wigner couples everything, we don't have any material records because everything has been destroyed. He's going to measure, yes, maybe I should have said. So Wigner is going to measure in this basis, which is a complementary basis, right? So he's measuring the whole thing in the basis defined here, the up-down basis, and the friend measured in the plus-minus basis, right? So when Wigner is going to couple everything. So he's very able experimentalist. He's able to couple everything, recombine everything. So the friend is still, alive, but in this other basis. So this is all, you have to be careful with the assumptions you make because it might simply not be realistic. But if Wigner is able to do this, then we have to sum over virtual paths because everything here has been erased, doesn't exist. There are no records, and as a the consequence is that you cannot define. I mean, these probabilities are simply not defined. Joint probabilities of the friend having obtained an outcome and Wigner getting a different outcome. So here, friend obtains plus and Wigner obtains up. That the probabilities does not exist according to standard quantum mechanics if we don't have any records left. The records are erased or they're just destroyed, and it's exactly the same situation as if no measurement had taken place. Again, Feynman is not interested in the state vector. He's only interested in amplitudes. So we don't really describe what is going on in the meantime. But the conclusion is that the only thing that is defined are the probabilities for the Wigners, the super observer, and these are given by a sum over virtual paths, just as we just saw in the double slit example, that we have a sum over amplitudes when we don't look at the slit. We don't measure the slit. But now another possibility is actually to measure which slit the particle went through. So here, what does it mean? It means that whatever W does, he must leave at least one record of the outcome outside what he's going to entangle. So he can entangle everything you want. So here I put the printer. Outside could have been the friend. It doesn't make any difference. The important thing is that if you have a record with the measurement outcome of the friend's measurement, with the outcome of the friend's measurement left outside. So again, same situation, initial memory state, apparatus and spin. But now my curly L, my calligraphic L here is just going to entangle everything except the memory. And if I do this, W can measure again in another basis, this up-down basis, but everything is absolutely well-defined because I have the record that has been left outside the superposition. So it's just exactly like looking at which slit your particle went through. You can define the probability of the friend having seen plus. You can define the probability of the friend having seen plus and Wigner seeing up. And just the probability of Wigner seeing up, which is simply the sum over real paths now. So exactly the same slit example I gave you, right? So these are basically the two ways that standard quantum mechanics would deal with this Wigner type, Wigner-Friend setup. So the conclusion is that the Feynman rules, they constrain the Wigner-Friend scenarios, right? Because again, probabilities need to rely on physical records, right? We are not dealing with what happens in the agent's inner life and so on. If no records are left or they don't exist, well, basically you sum over the amplitudes and you can't define probabilities. And one of the rules stated, this is taken almost verbatim from the Feynman and Hibbs book, that the amplitudes are not additive information about the final state is in principle available, irrespective of whether some agent, some observer knows it's there or not. So this really puts consciousness out of the picture. So it may not be obvious to you, but by just taking the record outside, it becomes equivalent to saying that a measurement implies a collapse or a state update, a mixed density matrix. I mean, it's strictly equivalent, except that just using these rules, you kind of remain agnostic, right? You don't really state as per Feynman's view that what is going on inside, right? Okay. So now we'll deal with the more involved generalized Wigner-Friend scenarios, especially there have been a few suggestions recently. So the idea is that now we have many, or at least two Wigners and two friends. But other than that, it's pretty similar. I'm not going to discuss the details of these papers. What I'm interested in, what they have in common, is that they take the idea that the friend is making a measurement should be described by the super observer, by the W's, as unitary evolution, right? This is what they have in common. Other than that, they're not. They are pretty different. So the starting point is that QM, so I put some quotes here, applies at all scales, and that QM is universal. But then when they say that, they usually mean that linear quantum mechanics. As we just saw, that actually have two rules: one when you don't measure, one when you measure. So basically, this is a bit confusing, because if you say that QM applies at all scales, but you're just forgetting the measurement axioms, then it might be confusing to some people. So actually, this is not the case for Deutsch's paper. In Deutsch's paper, which is an older one, it's very clear from the start. So what Deutsch says is that, I mean, he thinks that quantum mechanics with the measurement axioms is logically inconsistent because it's like it needs to rely on something else, some classical level, on some special faculties of observers, maybe some tricks. And he wants to, his goal actually is to build some version of quantum mechanics, which would be only linear quantum mechanics, and that would be logically consistent, even if it may be wrong. This is what he writes. Maybe it's wrong, but at least it's consistent, and let's try to see where it leads us, to many worlds and so on. But it's pretty important to really specify what we're talking about, because you mean quantum mechanics is universal. Does it mean that you're just taking the linear part, the first type of evolution, or you're just also including what you learn in standard textbooks, that there are two processes, the unitary one and the non-unitary one. And this is confusing when you try to take far-reaching conclusions. For example, in this paper, the conclusion was that quantum theory cannot consistently describe the use of itself. But again, it's quantum theory without the specific measurement axioms. But still, this paper, maybe if it's conceptually not very clear, it's very clever in a very clever setup that they have used. So for those who know Hardy non-locality, so this is exactly the same states they use. If you don't know what it is, never mind, it's not going to be important. So again, now we have two friends here. We have first, laboratory 1 with my friend inside, who is going to measure a qubit, let's say, an atom, or whatever you want in this plus minus basis. And of course, the super observer, W1. And then you have this friend, the second laboratory, L2, and now the friend is going to measure another qubit. So basically, the idea is that you build an entangled state with qubit 1 and qubit 2, and she's going to measure this qubit in a different basis. And finally, W2, the observer, is going to measure this laboratory in a complementary basis, just as W1 will measure laboratory 1 in a complementary basis. So let's try to run a little bit the argument. So at t equals 0, we have this laboratory 1. We have in this version, actually what happens is that the two spins are in L1, and that the friend F1 will send the spin to F2. Afterwards. So we start with S1 in this state. So this is the state that is going to be measured by the Stern Gerlach here. After the friend obtained the measurements, so remember, we are describing what happens inside by a unitary evolution, because this is what we assume here. So after this first measurement, well, we have this friends apparatus that couple to spin 1, and friend apparatus that couple again to spin 1, but now in state minus. And we have a unitary gate that will change the spin, the state of the spin is 2. So if if it's plus, if spin 1 was plus, then spin 2 becomes down. So again, I'm giving you this, remind here, the basis. We just change the basis. We have jumped to complementary bases all the time. And if the spin 1 outcome is minus, then we have plus for spin 2. And now we have the entangled state we need to run the argument. So the idea is that F1 sends S2. So again, in the states down or plus, depending, well, correlated with spin 1 being in state plus 1 or minus 1. So now F2 will measure her spin in this up-down basis. And you can write the overall state as in this way. So you just assume here that you just take L1, assume you had the apparatus for the measurement of spin 2 in some ready state, and you include all this in the compound notation. So this means that lab is in state in which everything is correlated with the spin in state plus, and this is simply the entire lab is correlated with spin 2, qubit 2 in state down. And this is how you can write your state after the measurement. F2 measured her qubit, her spin in this basis, right? So I reminded here. Now, the last step of this clever arrangement is that the external observers, the W's, are going to measure the labs, the respective labs, in a basis complementary to the one in which each of the friends made the measurement. So W1 is going to measure L1 in the basis up, down, because the friend measured the basis plus minus, as you remember. So again, I give you here the very simple relationship between both bases. W2 is going to measure L2 in the basis plus minus, because as you remember, the friend measured in the basis plus minus, and the basis, sorry, so W2 measures in the basis plus minus because the friend F2 measured in the basis up, down. Okay, so it's complementary, each time it's complementary. And right, so this is another way of writing the same state that I just discussed a few seconds ago. And now what they tell us in this Frauhiger and Renner paper is that you get a contradiction. So how do you get a contradiction? Well, if F2 obtains up, then necessarily F1 obtain minus. So this is by construction, because this is what we asked the unitary gate to do. So this is always going to be realized. Now we know that if W obtains minus, then this means that F1 obtained plus. So you look at W2 obtains minus. So this would be the state here. So you see you have this, and so minus is only correlated with the plus state. So this is correct. If W1 obtains up, then we're told that necessarily F2 obtained up 2. And so you can see it from here again, or from here, which means that this up state for W1 is only correlated with up state for F2. And then this implies that you cannot obtain well, the super observers cannot never observe W equals up and for well up for W1 and minus for W2. Because of course, if W1 obtained up, then F1 obtained minus, but if F1 obtained minus, W2 equals minus cannot be obtained. So this is what you would tend to conclude. But of course, if you look at this state here, you can see that the outcome is possible. The outcome W1 equals up and W2 equals minus. It's here actually, and it just has a probability of 1/12. So this is yeah. So this is the contradiction. So mathematically, so those who are familiar with Bell inequalities, or more generally non-contextual inequalities, well, this contradiction is totally expected. It's expected because what happens in Bell inequalities, well, you assume the existence of hidden variables, and non-contextual inequalities, you assume the existence of specific form of value abscription, that is absolute value abscription, and absolute meaning that irrespective of what you measure, so non-contextual. And once you do this, then this implies the existence of joint probability distributions, but the existence of such probability distributions are denied by standard quantum mechanics. And so this is where you get a conflict between the existence of joint probability distributions and, well, for example, when you measure observables that don't commute, you can't define. Quantum mechanics, by definition, excludes the existence of probability distributions. And this is why you have to actually add the amplitudes. So here we don't assume hidden variables, but the way they use quantum mechanics, so here quote quantum mechanics, linear quantum mechanics, implies the existence of joint probability distributions, because it implies the existence of the measurement outcomes for the friends. But this is denied by standard quantum mechanics. Standard quantum mechanics tells you, at least according to the rules I gave you, that no, well, they don't exist. If you just sum over the amplitudes, you don't have outcomes that you can that allow you to define probabilities. So then the next step is to see whether what is inconsistent is quantum mechanics and the existence of objective facts, or whether we have been running here some Wigner-Friend scenarios in a way that violate the standard rules of quantum mechanics. And so, of course, you know my position. Now we can easily get it, because according to what we have said before, standard quantum mechanics needs the measurement axioms, and if we have these measurement axioms, then clearly the way these Wigners-Friend scenarios are run violate the rules of quantum mechanics, the rules that I just gave you. So this is, well, probably easy to see, I guess, at this point. We just said that the amplitudes are never added if we have distinct and final states, and they're never added if information about the final state is in principle available. And that doesn't depend on whether the agents know or don't know what happened or are conscious or not conscious about it, right? So this implies that the amplitudes for the F's measurements should not be added if the F's made, genuine measurements. Because if we add the amplitudes, then this means that the material records that carry the F's outcomes do not exist. So maybe they have been erased, but it's impossible to, if you erase every outcome, if you erase every record in the universe, including the friend's brain about this measurement outcome, then how can you claim that measurement even took place? So, if you have a measurement without the measurement outcome, is it still a measurement? I think standard quantum mechanics is right in saying that no. I mean, you need the second rule. You need to do something special with measurements. And the underlying point is that quantum mechanics is a physical theory. You need to rely on records. It cannot just rely on the agent's inner life to close, to ascribe values to measurements. So it has to rely on material records. Yeah, this is the view that, according to us, is implied by the standard rules of quantum mechanics. So how would you run Wigner-Friend scenarios compatible with the Feynman rules? Well, the two main scenarios here are either the friends measure and then the W's, the super observers measure, or just only the W's measure. In the first case, let's say the F's measure and then the W's measure. So again, if the F's measure, it's genuine measurement, means you have a record, and the W's cannot, I mean, if they are extremely able, they cannot touch the record. The record is outside, so I put the printer outside. This means that the W's cannot engage the entire labs. There has to be, the records have to be protected if you want to define a measurement. Once you do this, then it's not a problem to run the argument because now you can define in a perfectly reasonable way the joint probability distributions. They're here and you don't get any contradiction. You obtain any probability you want by marginalizing. So you have joint distributions are defined thanks to the records, and then you can just sum over the marginals and get the probabilities you want. Like, for example, a probability for F1 saying up, W1 saying down, and so on. So you can define any probability you want, and you don't arrive at any contradiction. Another different scenario now is that you only have records from W's measurements. So here, the memory is like screwed up by W's measurement, and here too, the memory associated with this lab is screwed up by W2's measurement. Well, in this case, it's as we just saw the slit example, the two slit example before. There are no records. I mean, the records have been erased. It's like no measurement taking place. You have virtual paths. You don't know which slit your particle went through, and you cannot define the probability of having gone through a slit because it's you just have to sum over the amplitudes. And now you can again run the argument here, but you don't get any contradiction. You have different cases. If only records of W's measurement survive, then you can't define probabilities for the friend's measurement, right? So if we follow Feynman rules, that we claim are the rules of quantum mechanics, you constrain the scenarios, but you don't get any contradiction of any sort. So I have a few minutes, so just show you one more thing, is like how you can peek into the friend's lab with weak measurements. So even if you don't know what weak measurements are, this is not very important. The idea is that there is an open channel within that connects what happens inside the lab with a very small interaction to the outside world, right? So it's sealed except at the very end. Still, the labs are still sealed, except at the very end, and you have couplings very weak. So in addition, again, so this is in addition to the measurements done by the friend and by the W's, by the super observers. In addition, you have these weak, very weak couplings that do not change the evolution, the entire evolution. So actually, that does change to first order, but since the probabilities are to order 2, it's like it's not reflected in this very small change is not reflected in the probabilities observed by the agent. And so the whole idea is that you have these additional pointers, and so this again. So again, you have the friends and so on. This is the measurement apparatus that W will use to measure the lab. But now, so this is the weak coupling. So this is an additional pointer that W has that is kind of protected until the very end of the whole experiment. And at this point, at the end of the experiment, the super observer, once it has measured the state of the lab, will look at the state of this pointer. So what will the state of this pointer tell him? Well, it will tell him if we turn on and off the interaction at a specific time. So after the measurement took place, after the measurement for the friends took place, we just turn on this unitary interaction at this time. Well, basically, it will tell him if this pointer here will pick up the state of the pointer inside the lab. It will tell him if it's in a superposition or not. So the point is that even if you just apply unitary quantum mechanics, so the linear part of it, you will see that so phi 1 is the state of this pointer. So he knows, Wigner knows the state of this additional weakly coupled pointer at the beginning, and at the end, well, it's the state will need to make a lot of measurements to really measure what the state of this pointer is, but it's not going to be the same thing if there is linear superposition or if there isn't. So basically, this will allow W1 without F1 telling him anything if he saw the F1's pointers in a superposition or not, just by looking at his weakly coupled pointer. And so again, if you just run linear quantum mechanics, you will, W1 will see that the pointers here were in a superposition. So it will be surprising for him to hear the friend tell him that she obtained a definite measurement, because according to him, everything was still entangled, according to him, according to the coupling resulted from here. And right, and the same holds for, I won't have time to get into the details here, but the same holds for W2. So basically, it's kind of a problem to think that the friend will obtain, according to linear quantum mechanics, a specific outcome, but without interacting with her, W sees that everything is still in a superposition state here. There is no definite plus or minus. His pointer clearly shows that. So it's called a weak value, what he observes, but we don't need to know that here. So he will, through the weak value, the motion of the pointer, he kind of sees that everything is still in a state of superposition. And so even if you think there are observer-dependent facts, so then it's you need really sweeping assumptions to kind of explain that the friend has seen an outcome, but the super observer still sees a superposition, and they're basically dealing with the same theory. So again, unless you somehow use consciousness because the current, this type of experiments, the newer ones, they tend to kind of forget about consciousness because, maybe it looks silly, it's not politically correct, whatever. So they just say linear quantum mechanics. But the point is that if you don't use consciousness in the sense that the friend is conscious, so whatever Wigner is not, so he will still see superposition. If you don't use consciousness again as an argument, then this is, I think it's a big problem to just claim that linear quantum mechanics is sufficient to account for measurement outcomes. Yeah, so this was my last point. So now we can conclude. So take-home messages. So I hope you have learned what a Wigner-Friend scenario is. So you have a super observer that is measuring an observer that is making a quantum measurement. This is what a Wigner-Friend scenario generically means. Well, there are ambiguities when accounting for measurements, and so Wigner at some point suggested that maybe consciousness could play a role, so following the lead by London and Bauer. Well, the recent renderings of these Wigner-Friend scenarios, they don't deal with consciousness, but we are told that there are observer-dependent facts and so on. And it's strictly, actually, as I try to convey messages, strictly equivalent. I mean, you can have observer-dependent facts, but it has to rely on consciousness because otherwise you do have a problem. This is what I mean. So standard quantum mechanics deals with Wigner-Friend scenarios by constraining the scenarios that are valid because measurements are linked to material records. This is, I think, very clear if you take Feynman's formulation. So the condition here is that W's must not destroy the friend's record. So even if you think, because maybe you can also think that it's impossible. Feynman was, again, not especially interested in speculating on what happens because he kind of says we can't know. But the idea is at some point amplitudes play no more role. When you have a measurement, amplitudes they just don't play any role, and you're just left with real paths. And so this is an important point. We also briefly saw that weak measurements allow the super observers to peek into the friend's lab and kind of guess what is the state of the friend's lab. So the conclusion is that the Wigner-Friend scenarios that lead to inconsistencies or observer-dependent facts between W's and F's account are incorrect from the point of view of, well, standard quantum mechanics. Now, of course, it gets interesting because maybe standard quantum mechanics could turn out to be wrong. Basically, we don't know. We have this strange measurement axioms that seem to work perfectly well, but they may turn out to be wrong at the end. So this is still interesting. So this is the result. All this talk was just based on a joint work with Dimitri Sokolovsky at Bilbao. I didn't give any references, but if you look at our papers, you will find the references of the papers I cited, and also a dozen of other papers that have kind of discussed these last results. Okay. So thank you very much. I will now stop sharing.
Thank you, Alex, for this very interesting and beautiful talk. And there's only one question at this moment. Can you read the question now?
Yeah, read the question.
Yes. How do we know is information about path is available or not until we measure? Question from the view of double slit, I think.
How do we know in which case?
How do we know the information about the path is available or not until we measure?
No. Well, we have different setups. In this setup, we don't have any information because we're not doing anything. So in this case, we have we have to know sum over paths. You have to take into account all the possible paths and that reach the detector, right? So you just sum over the amplitudes. Now there is another situation in which you add detectors here that couple without, of course, changing, let's say, the path. So that can be polarizers. It can be another degree of freedom. It can be, it's which path information you can have without changing the dynamics of the particle. But this, again, is now you have added a measurement apparatus, let's say, an additional one, and then you can know. You can know by looking at the end. Once you detected the particle, you can look at the state, if it's n or y, and basically you will also not get superposition. You will get the sum over the real path now. So if you know, you don't get interference. This is something that we all know, right?
There's one more question that, explain the legitimate conclusions of Wigner-Friend paradox. Legitimate conclusion.
No, I think it's the legitimate conclusion, I think, is that quantum mechanics has a special rule for measurements, and you need to take it into account. So it's understandable that you would like to get rid of that rule, and if you get rid of that rule, so again, what are the two rules? It's either unitary evolution. So it's Schrodinger's equation, and when the system is not measured, and something different that you can describe by a projection in Hilbert space, or by just having memory quantum states of a memory of a record that is left untouched. So at the end you trace over it, but that doesn't. Okay, the technical cuisine is not important. The important thing is that you have two types of evolution: a unitary linear deterministic evolution when you don't measure the system, and something different. So this projection when you do measure the system. So that's the legitimate conclusion, is that you can't forget the evolution of the second kind. And if you try to ascribe measurements outcomes without using this evolution of the second kind, I think you are led to problems. This leads you to problems and inconsistencies. And even though I recognize that this is, the existence of this rule is you can't really account for it. You need to use it, but it makes the whole thing look logically inconsistent. But at least it's experimentally relevant. So we have a kind of a choice. If you want to be logically consistent, it looks like it doesn't really work. Although I didn't dwell into the specific many worlds version, because this is the only thing that could work. You could have a many worlds version of the Wigner-Friend paradox, but then you have to account how when the agents meet again, something has to change. The memory state has to change, because otherwise it won't work. So I think the legitimate conclusion is that we have two types of evolution, and we need to take both into account. And measurements are special, and we don't know why, but we have to take that rule seriously.
Okay. So maybe this question is not that relevant. Ankit Raj, what do you want to say actually? You're here, you can ask directly. Hello, Ankit, can you ask directly? Your question is incomplete. Okay. So maybe he wanted to ask, maybe I have a similar question. What is this, your work related to the other works? For example, this Bruckner and this Weissman's work, they have also discussed about these things. And also the Zhukovsky also talked about it.
Yeah, so basically this is what... I didn't hear that. It was I don't know if it was a question. So basically, what I was saying is that all these Bruckner works, it's Frauhiger and Renner, and yes, Feynman also. I heard his lecture at the beginning. Well, I followed it on YouTube. I wasn't able. What they have in common is that they forget that measurements are special. They just say QM applies at all scales and QM is universal, but they mean quantum mechanics without the special rule for measurements. So the claim, the conclusion we can reach here is that if we use textbook quantum mechanics, as Feynman taught this to his students, then what they do is not valid, because they ascribe measurements by just using universal unitary evolution without the measurement action. So this is it's related in this way, that they don't use the measurement axioms. They say that for the super observers, they should just use linear quantum mechanics, even though the friends obtained measurements. And we are saying here, well, no. If the friends obtain measurements, we have to apply the rules of quantum mechanics. We need records, and we can't just sum over the amplitudes. So that's
the problem. This is the main issue of the Wigner-Friend paradox. Because if friend gets the information, and it is a result for the friend, it is not a result for the Wigner. So how you can expect that Wigner should also use this, whether the measurement is done or not? This record he should use, because he can only use the whatever he has the access about it. Friend has the access about the record, but Wigner doesn't have the access of the record. He has no idea about the box. So how he can use the second rule of the measurement theory?
So this is the main point. So this is actually the main point. So Feynman and I think standard quantum mechanics, the one you learn in textbooks, tells you that it's not relevant to the agent's personal experience. You see, this is rule F here. The amplitudes are never additive information about the final state is in principle available regardless of whether this information is known or used by an agent. So if you have a measurement, you need a record, and this is a material record. It's not related to the agent's experience. What I tried to say is that if you think it's related to an agent's experience, and so you apply different rules, you get a contradiction. And you get several types of contradiction because the record obtained by the friend outcome does not exist anymore anywhere in the universe if you don't make this F rule. So if you don't apply this rule here. So the friend obtains an outcome, so Wigner doesn't know, but then it's going to manipulate the friend's entire laboratory and so destroy the records. So where does this record, so there was a measure, the friend made a measurement, but there's no record left anywhere in the universe. The friend's brain has been changed to another state, so everything has been erased. The records have been erased, the printer has been erased. And so the question is whether you can still define a valid measurement under these circumstances. And I think textbook quantum mechanics tells us no. Well, Feynman was very clear with this point here. And if you think about it, I think you also would reach the same conclusion. It's very hard to even define a measurement if no outcome exists. So of course, it becomes a bit of a philosophical question, right? What happened to the experience, the friend's experience, if she obtained a measurement and then everything disappeared. But the point is that the user of quantum mechanics, they can't make anything out of it. If you want to define a measurement without an outcome, then it's not a measurement. There's nothing, I don't think that you can get out of that. But of course, this is debatable. So.
Okay, maybe I should read your paper once. Francisco has the question. Francisco, can you ask directly? Francisco, are you here? Okay, sure. So Francisco has a question that also in classical statistics, we find two kinds of evolution: the linear evolution of predictions, the noisy channels, and the nonlinear evolution that happens during an update, inference. Should we be concerned?
Yes, so of course, this is again a very relevant question. So in classical mechanics, we actually know so we have these theoretical terms. We know that some terms refer to the material world, and some terms are let's say what they call epistemic, means related to information. And this is clear, like when I just gave the example of this classical action here. Classical action, in the point of view of classical mechanics, is just an epistemic term. It's going to describe things. And so, I mean, a statistical distribution can jump once you know something. So this is not a problem in classical mechanics. The problem in quantum mechanics is that we don't have any idea of what we are describing with our theoretical terms. And so this is why some people will say, oh, the state vector is just pure information. It's not related to anything that is happening in physical, physical reality. And others will say, oh, well, no, the state vector describes exactly what's happening in reality because things don't take really place in space-time. And in between, you have a lot of other positions. So the thing is that even if you have a purely epistemic approach or information-related approach, psi is state vector is pure information, there's the question that Bell asked, it's information about what? So because even if it's going to just give you an information, and then of course you can just update it as you want, it's still describing things that happens in the real world, in the physical world, right? So the situation is really different. So classically, I don't think you can. You don't have to bother. Quantum mechanically, you have to kind of, make specific assumptions on what psi is, and then you may bother or not bother. So of course, if you assume that psi is purely knowledge related, you won't bother. But still, you need to apply the rules in a correct way.
Thank you. And this guy formulated the question again. Maybe he has a very okay, Dipankar, you want to ask questions?
No, the other one who asked the question, you take his question. I can go.
Okay, sure. The student says that does quantum theory apply at all scales, including that of observers? And then he's saying that new light on this fundamental question has recently shed through a resurgence of interest in the long-standing Wigner-Friend paradox. I mean, he wants to ask, I think, what is the Wigner-Friend paradox, actually, that is proving that whether quantum mechanics applies to all scale, including the observer.
Yeah, so this is of course a very interesting assumption. So the idea is that maybe quantum mechanics can apply to all scales as long as we can manipulate coherently, the 10 to the Avogadro number of particles. And so in principle, you can assume that. I think it makes sense to assume that in principle, you could, so again, when we say quantum mechanics applies at all scales, I mean quantum mechanics with my special measurement axiom, not just linear quantum mechanics. Now, does this make sense? Can you really think that you can manipulate this very high number of particles coherently? Probably not. Probably not. It's just like in classical statistical mechanics. If you just have this blue gas and red gas, and then you mix both of them, in principle, you have a very small probability that after they are mixed, one will appear. They will separate again. But in practice, it's never going to work. And so maybe we are hitting here the limits of quantum mechanics, right? So this is exactly when do amplitudes, the question is when do amplitudes start losing their role? So this is very relevant in connection with gravity, how you will include gravity. Do you have to include the amplitudes, or do the amplitudes lose their role, right? And so of course we don't know. So we don't know. This is the type of thing that is very interesting to investigate, especially from the experimental point of view, because you can easily assume that quantum mechanics will apply to these very complex systems, but you can very hardly think that in practice this will be possible. And of course, if it's in principle possible, in practice not possible, it means your theory has a limit and you have to understand why. So personally, I don't believe it applies to.
Okay, thank you.
Yes, so Alex, so the general message you conveyed about Wigners Friend, about the record existence being crucial for a measurement without an outcome is not a measurement, and the record existing for Wigners Friend but not for Wigner. Now, what is the crucial role being played by the use of weakly coupled probe in this general message or argument about Wigner? What is precisely the role? Means what additional feature is being illustrated by your use of weakly coupled probe?
The additional feature is that if you think that you should apply linear evolution, then your weakly coupled probes will show you that the friend lab is still in a superposition, right? So
show that the superposition to Wigner with respect to Wigner.
Right, with respect to Wigner. So with respect to although you are actually coupling, so that's the subtlety, is that you are coupling Wigner's probe that is outside the lab to what's happening inside the lab. And so it's telling Wigner that inside the lab we still have a superposition. But the friend, in principle, I mean, according to this argument, has obtained an outcome. So you have to explain why the state of matter that is coupled to Wigner's probe outside indicates a superposition, while the friend has obtained a definite outcome. So this is, it gets a little bit tricky because, I mean, you need then to somehow put back consciousness into the picture, because the friend is conscious about the outcome and Wigner still is not conscious. So this is the only way you can actually solve the problem in my view. And I don't want quantum mechanics.
So what is your way out? What way out you suggest? That means what option do you present?
Well, my way out is again to remember that textbook quantum mechanics tells you measurements are special, and so you cannot use linear evolution to describe the friend's measurement. This is the main message. We have, if a friend makes a genuine measurement, we have a material record that is not going to be coupled.
So then in that case, Wigner it won't be legitimate for Wigner to apply the whole thing and conclude the superposition, the existence of superposition. This is what you say. That if the record exists for friend.
Right. If the record exists, then
record exists for the friend. Okay.
Yeah. So if the record exists for the friend, no. If it's a measurement, it has to exist for everyone. Yeah.
Yes. So that
because if Wigner destroys the records, then there's no measurement outcome anyway. So and then if the record exists for everyone, the weak values will indicate this. They will not indicate a superposition. So to me, it makes sense. I mean, it makes it. It's consistent without, again, introducing consciousness into the picture, which I think we should avoid. But and is unavoidable if you just think that linear quantum mechanics is sufficient to describe measurements.
So there can be a way of testing this? Can there be a way of testing this, because you are predicting a coherent? If the record exists for everyone, then the question whether the superposition is existing or not really, it's an objective issue. So one can ideally test it.
Yeah, we can think about tests, but actually just the idea that
no, I'm saying in principle it should be a testable.
Yeah, in principle, just the idea that there's a superposition in principle can be. In practice, again, if we're dealing with macroscopic observers, the interference. So maybe there's a way out, but I mean, if you just want the interference of laboratories, this is untestable because the wavelength is going to be so small that not even the smallest wavelength can discriminate this. But maybe there is a way out with weak measurements to test this. This is I agree. Yeah, this is an interesting observation. Yeah.
The whole point, actually, I mean, I'm confused with the whole point, because you are saying that the results should be for everyone, but this is the point of the quantum theory, that this is the observer dependent thing. So how? I mean, when I have to read the paper, otherwise I may not understand.
So what are you worried about? So
I'm worried about that you are saying that I mean the record, measurement, when outcome is not obtained for everyone, then this is not a measurement. So this is the things I'm really not.
Yeah. So no, I'm saying that if the record is destroyed, it's not a measurement, because so the friend makes a measurement. And then everything is destroyed when the Wigner measures in a different basis. Yeah. Everything destroyed means that the printer becomes a different thing. So it had the plus, printed a plus, there was the outcome, but then a minus, so everything is going to be screwed up, and the friend's brain is going to be screwed up, and there's nothing left of that measurement. So how can you even claim there has been a measurement? So this is
so you are saying that when friend did the measurement, if he knows the outcome, and then
that's the point. I'm saying that the only way out is to put consciousness back into the picture, that there is something outside the material world, and that this outcome lives outside the material world, because every material particle that carried the outcomes has been destroyed, has been erased. And so then the problem is, well, how can the friend still, so the friend won't have any memory of the outcome she obtained, because everything is going to be destroyed. I mean, if you make a measurement, you don't always know that. I don't know on June 29th.
I got your point. I got your point, but I don't
you will consult. You will look at your computer. What did I obtain on June 29th at 4 p.m.? Well, I obtained this result. But now everything has been destroyed, so erased. So this information does not exist anywhere in the universe, except if you assume there is something outside the material world that. And I don't think quantum mechanics can do. I mean, there may be, but quantum mechanics certainly cannot describe it. I'm not saying that there's nothing beyond quantum mechanics, certainly not. But yeah, so this is, again, I think.
Yeah, I got your point, but I don't know whether I'm convinced or not.
Okay. That's
that needs time.
Yeah, we need to, we can discuss that again.
Yeah. Sure. Dipanggata, you want to say something?
No, it's okay. I don't need.
Okay. It was before.
Okay.
Okay, so is there any more question anyone wants to ask? I think there is no more questions. So Once again, Alex, thank you very much for
Yes,
this
Alex.
excellent talk,
Thank
and you give some food for thought to us. So we'll discuss again later on here.
And again, thank you very much for organizing this call.
Thank you, Alex. Okay.
Okay. Professor Paringe, are you here? No, I mean, he's listening when he talks, so hard for him to stay in when he talks.
Yes, so Alex, thank you, and see you.
Yeah, thank you, Alex.
Yeah,
We'll see you soon.
get
Yeah.
back in touch.
Okay, bye. Yeah.
Bye-bye.
Okay.
Thank you. I'm good.
Hi, Ashok.
Hello, sir.
I am here.
Yes. Yeah.
I still 2 minutes are there.
Also here, huh?
Hello, sir.
Hi.
How are you?
So far, so good.
So far, so good.
See, आरपीजी को आप देखोगे तो आरपीजी पूरा प्राइम मिनिस्टर के दोस्त बन गए हैं. But looks like Ashok has lost some weight, huh?
No, sir. I'm maintained actually. I maintained the same weight like for last 8-10 years.
Oh, very good, very good.
Yes. I'll start sharing, sir.
Just,
So RPG, you can start. Introduce.
yeah, just 1 minute, Prashant. Yeah.
Oh, yeah. Just. Or.
But let me anyway. मैं थोड़ा सा बोल देता हूँ.
Yes.
RPG आप बोलोगे या मैं बोलूँगा?
आप भी बोल दीजिए, क्या फर्क पड़ता है? नहीं तो मैं बोल देता हूँ बस. मैं बोल देता हूँ. जस्ट 2 मिनट रुकिए प्रशांत जी, अभी टाइम नहीं हुआ इसलिए मैं बोल रहा हूँ. 29. We should always wait 2 minutes extra rather.
ठीक है, no problem.
Start at 4:32.
No problem. अच्छा, Ashok, what is your wife doing now?
Excuse me, sir.
Your wife.
Yeah, she is a women scientist here in IIST actually.
Very good, very good.
Yeah.
Any other input about this Riemann hypothesis?
Yeah, she has gotten very nice result. I think she had completed and then she is communicating now the paper actually. She has sent paper to PRL and then she got referee comments. And then after that, editor thinks like it should go more specialized journals. She is trying to find a right journal actually. Now, first paper they have published in PLB, right? So second paper she wanted to, because it's like a completing the model actually. And she wanted to go for like PRL or other journal, but they said, okay, the first part is published in the other one, so go to specialized one. Like C got, of course, it was reviewed 2 times.
Achha.
And then C will be like, C sent to the PLB, and then the like editor was like, that was not, I think it didn't go to right editor actually. He himself said, okay, again, this one doesn't fit to PLB. And C just communicating with that, first part is published in PLB, why it is not fit like that.
Tell me, there was some news item about this from Hyderabad, from Hyderabad.
Yeah.
I know this person.
Oh, you know him?
Yeah. He used to come, he's a mathematics oriented engineer, friend of Professor Srinivasan.
Yeah.
So he has been, I know, doing varieties of things on the side because he likes to do mathematics optics as a hobby.
I see.
So I have not gone through his proof, but you can ask Vivek. Vivek knows about him.
Okay. But that one also not published, right? Anywhere?
No, not published.
Even in
not
archive.
Published. That's right.
Yeah.
He has not made a big news item of it.
Yeah.
The private institutes, they highlight these things. They
In fact, Pushpa has not sent that to archive yet. Actually, she said, okay, let's get some comments and then submit to the archive. Actually.
Okay, I think we can start now. It's 4:32.
Yeah.
So, Prashantji, with your permission, should I start?
Yeah.
So all of you are here, I think. How many? 143. We have enough numbers. Okay, 143. So it's a great feeling to introduce your own student on such a platform. Really. So feeling very nice, very happy. And I will not read a reference letter for Ashok. Okay. There are so many reference letters. So Ashok did his PhD from PRL and finished his PhD in 2001. Worked on orbital momentum of light, like beams, light beams carrying OM, how they are scattered through scattering medium and its properties after scattering, intensity correlation, other and other properties he studied. From there, he went to University of Sao Paulo and worked with cold atoms as well as OPO, optical parametric oscillators, with a view to study quantum information processing using continuous variables of atoms and light. And then in 2015, he went to US, University of Oklahoma, and there he worked on quantum enhanced plasmonic sensors. So he has worked in a variety of fields, starting from small setups to big setups, okay, atomic systems, and as well as pure optical systems. And he has good number of publications, already more than quarter century he has made, okay, at such a very young age, okay. Very soon he'll be completing century, okay. And his research area basically includes primarily experimental quantum optics, quantum sensing, quantum enhanced imaging, and quantum plasmonic sensors, bright squeegee states, EIT, electromagnetically induced transparency, and of course, the orbital momentum of light. So you can see that variety of fields it dwells into. And today is going to talk about special quantum correlation properties of bright twin beams of light. You will see how you can study entanglement between two bright twin beams of light, like squeeze states and all those things. You will listen from him. And so here is Ashok. Ashok, over to you.
Sir, it's a great honor to be introduced by supervisor. Of course, I would like to thank Professor Panigre to giving me an opportunity to talk here. So, yeah. So what I'll be talking about today is some of the work that I have been doing in past couple of years. This is a project I was involved, and then of course I'm continuing that. So the idea is what we want to address actually. We want to address the spatial quantum correlation properties of bright twin beams of light. of course, what I will do in this 1 hour talk, so I'll start with like a fundamental aspects. What is like basically what are special quantum correlations? And then how they are evolved over the time and how they will be useful actually. So I will like in the first half of my talk will be kind of reviewing the previous work and then giving some basics. And in the next part, I will give some of the results on the bright twin beams of light. So to start with, I would like to motivate you why one should care about the special quantum correlation properties actually, and why they are important. So you will see when you will go over the talk, then you will see that they are useful in many areas actually. So one of the most prominent area for the special quantum correlations is quantum imaging. Of course, they are equally important in quantum sensing and quantum metrology and quantum information processing. So these are the application point of view. But on the other hand, they are important in the fundamental point of view as well. For example, they provide a test ground to play with quantum physics or to learn about or to understand the entanglement, Einstein-Rosen paradox and all. So with that motivation, actually, if you go over the talk, then you will see that, okay, yeah, we can be motivated to learn special quantum correlation properties to understand these facts actually. So if you are interested more to know about the special quantum correlation properties, I would like to advise you to go over these review articles. One was from 2010 and one was 99. So this was like early review, and after that, this was covering the the state of art until 2010. Of course, after that, a lot of studies are going on actually. So the outline of my talk will be like this. So what I'll be doing, I'll be talking about how do we define special quantum correlations, or what do we mean by special quantum correlations. And then in next part, I will tell like how the special quantum correlation properties has been studied in spontaneous parametric down conversion, and then what are some applications, and then I'll tell you the limitations of what we can do with the SPDC photon pairs, and then we'll come to the bright twin beams of light, and then basically I'll tell you how do we generate the bright twin beams of light, and then I will come how do we detect quantum correlation properties with EMCCD cameras, and then finally I will end my talk by demonstrating that an experiment that we have recently done by demonstrating that Einstein-Rosen paradox with those bright twin beams of light in cameras actually. So to start with, as you might have seen so far, like so many talks has been happened. So most of the quantum correlation properties people dealt with, they deal with the temporal arrival of photons, or they study basically temporal correlations. For example, if you generate a pair of photons, or if you generate twin beams or pair of photons, and then what most of the quantum correlation or quantum studies we do, we detect these pair of photon over the time on the detector actually. We just look at when the photons are arriving on my detector, and based on that, what I get at the output, I will get a noise actually, because the photon arrival time is random, they lead to a random noise. Basically from the detector, I get a current, and then there will be random fluctuation over the current. So of course, if I have a pair of photons, basically correlated pair of photons, then the noise on the other detector will be the same actually. The fluctuation will be the same. So basically these noises will give me the temporal quantum correlation, or they will be like a correlated noise. So now what I would like to address here, so instead of just looking at the temporal degrees of freedom, just looking at the temporal arrival of photons, that what we can do, we can look at the correlation of the photons in the spatial degree of freedom. What I mean by saying that, so if I have a twin photons or source of twin beams, what I can do, I can collect, or I can get image of these beams and then look at the correlation in the arrival time of photons, basically correlation in the spatial distribution of photon in my beams actually. for example, one photon arrives here, its partner is arriving here. So how the photons in different spatial modes are correlated, that is the essence of spatial quantum correlations. So my time is fixed. So I will look at a spatial domain and then how my fluctuation in the spatial domains are behaving. That's what I want to study, or that's what I am concerned about actually. So now coming to the fundamental questions that, who gives those spatial quantum correlation, or where do they get those spatial quantum correlation? So this is very fundamental thing that you might have seen so far, that, if you want to generate a quantum beams or entangled beam or photon pair, for that you need a nonlinear process. Basically, you need a nonlinear interaction of your laser with a medium actually. And then that means what you have, your medium have to have these nonlinear coefficients, like appreciable these nonlinear coefficients actually. So based on these coefficients, you can have the process called chi2 nonlinearity or chi3 nonlinearity. So what the most, or the very, very popular technique is based on the chi2 nonlinearity. That is like a technique to generate the photon pair is chi2 nonlinearity, and that is based on the spontaneous parametric down conversion. On the other hand, one can generate, or one can use the chi3 nonlinearity also to generate the pair of photons. So here I'll first talk about the SPDC, or spontaneous parametric down conversion. In the latter part, I'll talk about how do we use the four-way mixing. So just if you were there in Professor G.S. Agrawal talk, so you might have seen that he is also using this four-way mixing in the atomic vapor to generate the entangled beams actually. It's along the line of the work I do or I did in US, or I'm planning to do here. So first coming to the spontaneous parametric down conversion. So as you know that, or you have seen, just for sake of completeness, I'm talking here. So in SPDC process, what you do, you have a strong laser beam, you pump your nonlinear crystal with a laser beam, and you generate your twin beams actually, or twin photons, and you detect these twin photons by detectors. So while generating these twin photons, what happens? Your crystal absorbs one photon, and then due to energy conservation, it emits a pair of photons. Of course, the energy, sum of the energies of this pair of photon has to be equal to the energy of your pump photon. And at the same time, they have to satisfy the momentum actually, or they have to satisfy the principle of conservation of momentum. So basically, if your pump photon goes in this way, your signal photon and idler photon should satisfy this condition. That is called phase matching condition. Now, if you very carefully look at these two phenomena, like one is energy conservation, other is momentum conservation or phase matching condition. So when you look at the energy conservation, one photon is emitted and then, one photon is absorbed and two photons are emitted at the same time. Basically, these photons are emitted at the same location in the crystal. So they have a common birth zone actually. So they have a common birth zone, and that gives a position correlation to these two photons. On the other hand, momentum conservation or phase matching conditions gives a momentum correlation. If one photon go in this way, other has to go in this way to satisfy the total momentum actually. So this gives a momentum correlation. So when I talk about the spatial quantum correlation properties, so I'm just concerned about position correlations and then momentum correlation. Basically, I image my beam on a detector and then look at how their momentums are correlated or how their positions are correlated. So that's the main goal. But now question comes again, how my detector will know that I'm measuring the position correlation or momentum correlation? Or how would I do that? How would I measure the position correlation and momentum correlation? So for that, you can use like a very, very simple principle of optics. that, as I said, twin photons are generated inside your crystal or inside your nonlinear medium. So their birth zone is the same. So if you use just a simple lens system, that simple lens system that can image the birth zone to your detector. That means your detector can give you the position information. Your beams are going this, you use a just imaging system, your imaging system can give you the information of the position correlation, or this kind of system we call as a near field correlation. On the other hand, for the momentum correlation, if you want to look at the momentum correlation, that means you have to go to complementary domain. You have to go to conjugate variables. The position, the conjugate variable of position is momentum. So you have to go to Fourier domain. And then again, very beautiful thing, this lens provides us. So lens provides us a Fourier transform. So people who are not aware of how to realize a Fourier transform in lab, it's very simple. If you have a convex lens, what you do, hello? Yeah, so what you do, you just, instead of just imaging, this lens was meant for the imaging, but other lens can give you Fourier transform. Basically, it will map your position correlation to the momentum correlation. So if you place a lens like this, F to F configuration, from here to here, the distance F, and from here to distance F, then ultimately what you get here is information of momentum correlation. So basically this lens maps your momentum position correlation to the momentum correlation. That's how you can get information of momentum correlation in your detector plane actually. So once we do that, of course, now we know that just a basic idea I gave, you can have position correlation, you can have momentum correlation just by using a simple imaging system or simple Fourier transform system, you can map these to your detector plane. Okay, that's like some experimental detail. Now I will tell you that, what these special quantum correlations can provide you. They are, if you look at the basic Einstein-Podolsky-Rosen paradox, that deals with the spatial quantum correlation. That deals with the position and momentum correlation. So basically, with this simple setup, you can show the EPR paradox. So again, people who are not familiar about the EPR paradox, I would like to introduce you that, in 1935. There was one of the strongest paper of 20th century by Einstein, Podolsky, and Rosen. Actually, they questioned about the completeness of quantum mechanics. What they did, they basically, they created an hypothetical experiment actually. They created an hypothetical experiment and they said, okay, if I have a pair of particles, with perfect correlation between their positions and momentum. They are perfectly correlated in their position, perfectly correlated in their momentum, then if you will see just now, then if that exists and if you put them apart, like if you send them, if you put like a space like separation between them, then such a perfect correlation can lead to an apparent violation of Heisenberg's uncertainty principle. And that was an EPR paradox. So how it happens, I will come to you. Just in very, very basic way, I have put here some equations. So if an EPR paradox or a state in the EPR kind of state, I can write like this. So I can write like an EPR state in position basis like this. So I have two particles, A and B, and both this XA is position eigenstate of particle A, XB is position eigenstate of B. So what does this state tell me? This state tells me if I make a measurement on position, and if that measurement gives, if I make a measurement on position of particle A, and if that measurement gives position X prime, then I automatically or immediately know the position of, so that's what this state means. Now, if I transform this state to the momentum basis, I just want to look at this state in the momentum basis. By using simple quantum mechanics, you can do it. And then if you transform it, then it turns out that the EPR state in the momentum basis looks like this. What does that mean? It means that if I make a measurement for momentum of particle A, if I get, let's say, moment P prime, then I immediately know the momentum of other particle as a P prime, actually. So then it looked like what Einstein said, or these people said that time. They said, okay, the particle B was like space-like separated. So it was, they treated both particles independently, and it looked like if I measure the particle A, then I can infer precisely the position and momentum of other particle. And it looked like that both A and B, or both position and momentum of other particle was precisely defined. But it was later on realized that this was, whatever the conclusion they made, that appeared, or that came because of they considered these kind of system independently, or they considered local realism actually. But later on it was found that quantum mechanics is not local actually, it's like a non-local actually. So these two particles, like they are related to each other, they are linked to each other. So if you do a measurement, you can discover the other particle. So the point is, of course, you are not, anyway, you should not, mislead, or you should not misunderstood that you are not violating uncertainty principle, because what they are doing, they are just making a measurement on only on one variable. You make one variable measurement on one variable, you make measurement on other variables. But it looked like if they were not connected, it looked like the other particle was already having the precise position and momentum, but it was not. It is not the case in actual scenario. So what basically we can do actually, or later on it was realized that if you can generate any state, if you can generate any state in which the inferred uncertainty is inferred uncertainty of position or momentum of one particle, provided you do measurement on the other particle, if the product of these two is less than h bar by 4, then this holds, or this satisfies the EPR argument. If any, you can find any state for which you can have inferred uncertainties in one particle, position of one particle and momentum of one particle, provided you do measurement on the other particle. If they satisfy this inequality, this condition, that means you have created situation like EPR argument. So this situation, in 1988, Margaret Reid and then Neumann shows, they theoretically showed that this kind of state can be generated in the light actually. So they proposed actually, if you look at the phase, if you do the phase and amplitude measurement of a light, then you can basically generate the EPR kind of state, or you can generate you can satisfy basically this kind of criteria. And later on in 1992, Jeff Kimball group had done this experiment, and they did the measurement, and they did instead of just looking position and momentum, they look at the quadratures actually. Basically, they mimic the position and momentum as the quadratures, and then with the quadrature measurement, they have realized Einstein-Rosen paradox. But the point is, until 2004, there was no, of course, what EPR assumption was, you have to take complementary variable actually. So complementary variable or conjugate variable, you can take any variable like a quadratures or other variables. But in its original form, like position and momentum form, was not realized until 2004, when Robert Boyd group at University of Rochester has realized this EPR paradox using position momentum entangled photons, generated with the spontaneous parametric down conversion. And of course, the idea was as simple as I explained in the very beginning slides. So what the point was, they have used a BBO crystal to generate twin photons actually. So you generate twin photons and you can get, first you have to get the position correlation. To get the position correlation, basically what you do, you just image your birth zone to your detector plane. These were the detector, just basically you image and you get the position information. And on the other hand, for the momentum information, again, they have to use a Fourier lens actually. They use a lens pair that basically Fourier transform their birth zone to detector plane actually. And moreover, this was just a photo detector, so it will not give you spatial information. To get spatial information, they scanned the photo detector. They kept one detector fixed and they scanned the other detector in the transverse plane of your beam actually. The other detector was scanned. And as a result, what they saw that suppose I keep the position x1 fixed and if I scan the other detector, then they saw the probability of like the coincidence or the probability of coincidence measurement appear to be like this actually. And similarly, in the far field, the same measurement is same, just you replace your system from imaging system to the Fourier transform system. And then they got the coincidence distribution like or probability distribution like this actually. Now, after then measuring the width of those distribution, they got the inferred uncertainty in the measurement of x2 provided the position of x1. Similarly, they inferred the uncertainty in the momentum of P2 given the momentum of photon P1, one photon as P1. And they got this product as 0.01, which is far below than what we need to satisfy the EPR criteria. So this was the first experiment that have demonstrated the EPR paradox in its original position and momentum form actually. Now later on, actually it was quite tricky because to get the whole spatial information, you have to scan your detector a lot, and then this takes a lot of time and time-consuming thing. Or then later on, like the group in Italy, France, and these groups tried to do those kind of measurement with the direct detection actually. So what the fundamentalist thing, the main idea remains same, but instead of just point detector, you can put in CCD cameras. So what this group did, so they again the same setup. Instead of this is just they wanted in this experiment, they have shown just measurement in one domain. Not they did not do the measurement in the near field and far field. They just did the measurement in the far field actually, or basically they measured the momentum correlation. And they detected both the beams by CCD cameras, and then of course I have like in a single shot I got the full information actually. Then what the idea or what they wanted to check, or their main idea was if the noise here and here are correlated, because if they are carrying some quantum correlations, their difference noise if the noise here and noise here are correlated, then if I do a difference measurement, I should able to subtract out the quantum correlated noise. So that's what they did. They measured a variance of the difference noise. They measured the variance of the difference noise normalized with the short noise actually. As a result, as you know that this factor is very important factor, because by measuring this factor you can characterize your state also. So if you have this factor greater than 1, this happens for the thermal state. If this factor is 1, this is for a coherent state, or this limit sometimes we call as short noise limit or standard quantum limit. But of course, if you can have this factor less than 1, then you have your quantum states, or you can have your squeeze state. So in this particular experiment, of course, they they did not show the EPR kind of paradox, but what did they show? They showed, the noise reduction of these beams below than the standard quantum limit or below than the short noise limit. This is the best that you can get with your laser or with your classical source. But with these quantum sources or photon pairs, they could reduce the noise down from short noise limit actually. Now, later on, of course, this was they did just a far field analysis, and they did not pursue for the EPR paradox and all. But later on, in another group in 2014 from France, so they have shown this kind of paradox with just twin images. So it was just continuation of the work that I have shown to you. So here, what they did, they used, instead of one camera, they used 2 EMCCD cameras. And what they did, again, here, the idea is you are pumping your crystal, you are generating twin photons, and you are using 2 systems. One is like an imaging system, other is Fourier transforming system. In this particular system, this was their Fourier transforming system actually. This detector was at F distance. Basically, in this one, they were getting the momentum correlation information. And here, in this one, this was an imaging system, and they were getting the position correlation information. And in this particular experiment, what they have shown that, of course, they could again show the EPR kind of criteria, and their product of variances was, of course, less than h bar by 4. Now, okay, then it was good, and of course, with the SPDC, people still trying to make better and better measurement or better and better noise reductions. So, meanwhile, I would like to motivate you that, of course, they were showing these fundamental effects, and at the same time they were targeting their experiment for the quantum imaging purpose also. For example, the previous Italian group that I have shown to you, they have imaged a faint object using these quantum correlation properties. So of course your twin beams are correlated. So they put one faint object in one of the arm of your twin beams, and then what, as a result, what did they saw? They saw that then enhanced resolution in their images. So basically they compared their result with the direct imaging. It was with the direct imaging, it was with the differential imaging. Differential imaging means the same setup, but instead of using quantum correlated source, they use a coherent source actually. And this was with the quantum image, with the twin beams. And later on, like just 2-3 years back, they have extended their setup for kind of microscopy kind of system where they focus their quantum beam to a sample slide where you have a sample like phi, and then they image this using another lens in your CCD camera. And this is again a proof of principle, and they compare the result of direct imaging or classical differential imaging with quantum enhanced imaging. As you can see that their resolution was improved by using the quantum imaging. So far it was, the SPDC photons were very good actually. They have given a significant insight into nature of spatial quantum correlation, and of course they help people to realize a proof of principle demonstration of quantum enhanced imaging. But there were some limitations also. One of the biggest limitations were the photon pair generated with the SPDC source were limited by poor conversion efficiency of your pump photon to the down converted photon. So this efficiency is pretty low. So that means if you want to get an image to get a good contrast or good image, you have to average your result thousands of the times actually, or you have to keep exposure time quite high actually. Moreover, of course, in the fundamental aspects, if you want to violate or if you want to show the EPR kind of system, then for that to get a statistically significant result, you have to take thousands of images to get a statistically significant result. So now questions comes, can we obtain, or is there any way to get spatial quantum correlation with a macroscopic beam or with a large number of photons actually? So that large number of photons where in a single shot, I say I have demonstrated EPR paradox, or in single shot, I have imaged or I have enhanced the imaging. So that is the fundamental question. So we have tried to answer that question, and we said, yes, we try to use bright twin beams of light generated with a Fourier mixing process, and that overcame some of the limitations imposed by the SPDC photon pair. Moreover, the results has some distinctive advantages actually. So the thing is, as I said, if you have a large number of photons in a beam, you can get statistically significant result in a single shot. And of course, if you have a more number of photons, as you might remember from Louis Davidovich's talk that he was talking about quantum sensing and all. So if you remember his talk, then if you have large number of photons, then you can enhance the signal to noise ratio. So of course, I would be happy if somebody gives me quantum correlated photon with a large number or in a macroscopic regime actually. So that gives you an added advantage. Moreover, the system that we are working with, that gives you a narrow frequency band photon. Basically, the photon pair you generated, you generate with the atomic beam, so they are narrow in frequency. So these beams are ideal candidate to interact with another atomic system actually. Another atomic system, why do I need to do that? Because if you want to make a quantum repeater or large scale quantum communication, then you have to have some quantum memories actually. So you have to store your quantum states in an atomic media actually. And if you have a state that is compatible with the atomic memory, then it helps you to have an efficient interaction. So these are some practical advantages working with this kind of setup. And more, in the fundamental perspective also, there are some advantage that, how if I scale up the number of photons, how these quantum properties they behave going from in different degrees of freedom in a macroscopic domain. These are this is just fundamental context. So what we have done in a past few years, we have tried to address some of the questions, and these are some of the references that we have worked with. So first, in 2017, we have shown that, of course, it's possible to obtain this kind of spatial quantum correlation with the macroscopic regime, and later on, we just we improved setup and showed many things. And then in the recent study, what we have shown the Einstein paradox with position momentum entangled photons. So I'll come to that. So to start with now, I'll give you, or I have given you enough flavor so far. People have generated this kind of, the spatial, people have studied the spatial quantum correlations with twin photons. Now we are switching gear from twin photons to bright beams. So how do we generate bright beams? For that, we are using a Fourier mixing process in a double lambda configuration. So what we do basically, we interact a strong laser beam with an atomic vapor, and then a strong laser beam and a weak laser beam in an atomic vapor. So in atomic vapor or hot atoms, what happens? Two photons from your pump beams are absorbed, and due to energy conservation and then Fourier mixing process, two photons, probe and conjugate, are emitted actually. Again, they are the same. The difference you see actually in the SPDC, there was only one pump photon was involved. Here you have two pump photons, but output again you are getting correlated photons actually. So now with the input beam, you stimulate the process actually. If you start with some input beam, that stimulates your process, and then you can generate your bright beams here actually. You use your detectors, you can see that these beams with your naked eyes actually. They can be power of up to 1 milliwatt actually. So you can do it. So now coming to little bit more deeper. So as I said, these twin beams have to satisfy the phase matching condition. So of course, some of the momenta of pump has to be some of your probe and conjugate or twin photons. So the mismatch should be as close to as 0. But if you do some calculation, you will see that, there is some tolerance actually. Of course, when you have this delta K is 0, then you get a maximum efficiency. But if it is like not 0, still you see some photon generation actually. So this phase matching is basically given by this thing function actually. And basically you have some tolerance actually. You can either go here, you can have some minimum angle or maximum angle of pump and probe actually. So what that leads, that gives like a kind of, that gives me a spatial bandwidth or angular bandwidth actually. So my pump beam is here, seed beam is here. So I can have, because of phase matching, I can have a spatial bandwidth or angular bandwidth where my twin photons will be generated. And very, very beautiful thing about this setup, there are techniques, other techniques also to generate bright beams like OPO or put a SPDC crystal inside a cavity, but these techniques have some limitation. One limitation is, here, if you put a cavity in a SPDC, then it just filters out it gives you only one spatial mode. But here you can have many spatial modes. What do I mean by that actually? So what I mean, if you use different profile of your seed beam, you have a probe beam going to your detector. If you make some pattern on your probe beam, then you can, if you stimulate your process by some pattern, then you can generate the same pattern to the other beam. Basically, if you look at, let's say here 200 numbers, so you can get the 200 number in the conjugate beam. So that means you can get like the twin entangled images. This image is entangled to this one because one you get here, other you get here. These are kind of entangled images. So these kind of multispatial mode properties can be preserved in this kind of systems. Moreover, now coming to the spatial quantum correlations, so the experimental setup, as I said, of course, there are some other complications, but in the fundamental point of view, it looks the same as I discussed in the very beginning slide. So this was just a source to generate my beams. And these were, in this particular experiment, what we did, we just did the correlation measurement in the far field actually. So these lenses were giving the Fourier transform of cell center to the EMCCD camera. Moreover, there were some complications while doing the measurement with the bright twin beams, because the thing is your beams are so bright actually. Your beams are so bright, and then when you say the correlation, you are looking at the correlation means you are looking at the fluctuations, correlation in the fluctuations. So how do I get fluctuation in this beam and fluctuation in that beam? For that, we have to use a trick actually. So what is that trick? So you have to acquire twin beam images in a fast succession actually, or in a very, very fast speed. Or what you do, what we have done, we have pumped our or we have pulsed our probe and conjugate. These beams are pulsed, and then what we did, we record a single shot. one pulse goes and it records a single shot image of my twin beams on my EMCCT camera. And then after a short time means like about 60 microseconds, I get sent another pulse, and that pulse gives me another shot of images, conjugate and probe. So they are just very, it's like a 60 microsecond time difference between these two. Then what I do, I just subtract these two consecutive images. I subtract these two images and I subtract these two images. And these images basically give me the spatial correlation, spatial fluctuation, spatial fluctuations. So how my intensity is fluctuating in those beams, that I get just by subtraction. And if I do look at just 1D plot, these spatial fluctuation appears to be like this. Now, as I said, we are doing the measurement in the far field. That means they have to satisfy the momentum conservation. So if one photon goes here, other photon has to go to diametrically opposite actually. So that means if one photon is hitting here, its partner will sit here actually. So just to get or to align the images or to align their spatial quantum or spatially correlated region. So what I did, I rotate this image by 180 degree. I rotate so that, this correlated region and this correlated region, they are just aligned together. They are aligned together. And now why I'm aligning, if you remember first Italian group experiment, what I want to do, I want to subtract those two images. So if I subtract those two images, then I get noise in the subtracted images. And that I want that noise in the subtracted images, I want to show that noise can beat short noise limit or standard quantum. Basically, mathematically, what I'm doing, I'm just getting two shots from one shot from these. By subtracting two shots, I'm getting the noise in one beam and noise in other beam. And then if this is my, let's say, probe noise, this is conjugate noise. If I do the difference measurement, I can get a difference noise. And I normalize this noise by the shot noise. And the point is, I want to show that this noise goes below than what is allowed by standard quantum limit or what is allowed by short noise limit. That's what we have done here. As you can see here, so this was our short noise limit or short noise measurement, spatial short noise measurement we performed with just a laser beam. And this was our spatial squeezing measurement. Basically, noise below than the short noise limit is called squeezing actually. So we have obtained the squeezing in those twin beams. And in this particular experiment, we have obtained the squeezing of 2 dB actually. And then of course the thing is, as I said, like the probe and conjugate region, or they are diametrically opposite. So I had to rotate one of the beam. But if I don't rotate, then they are like anti-correlated actually. They are not, if I subtract this and without rotating, they are anti-correlated. And then that lead to you an excess noise actually. So this is just without rotation, just to show that in the far field you get anti-correlation in momentum. So moreover, one fundamental question here also, we would like to address the question that what is the spatial scale of this fluctuation? You say that the probe beam and conjugate beam are fluctuating actually, but or if I have one photon here, what is the spatial scale or the part or the noise at this point will be correlated to which region of this point, or how big region at this images this noise in this point is correlated. For that spatial scale of correlation or spatial scale of noise correlation that we characterize or we call as a coherence area. So how do we do that? To get an idea of the coherence area, what we do, we just select just crop a small portion of one of the beam and then scan this over the other. Basically, we calculate the cross correlation of this noise with this, and then just keep scanning. And as a result, we get a cross correlation curve like this. The peak shows that it has, this is some point, it is correlated very short width actually. That tells you the kind of spatial scales of those correlations. On the other hand, when you repeat the same measurement with just a laser beam, if it was, if it was not a four-way mixing, if it was not a twin photon, if it was a laser beam, usual laser beam, you don't expect, if you just take two sorts of laser beam, there won't be any correlations. So what you get just a flat background. This was just a sanity check of our experiment that everything is going fine. So once we did this, then in the last part, what I want to cover, the next part we did now we want to look at like EPR kind of situation, or we want to violate this criteria actually. Is it possible, or can we violate the EP, or can we show the EPR paradox by using those macroscopically bright beams? Again, as I keep telling you, the fundamental system is same actually. So what you have to do, there are a lot of technicalities involved in those experiments, but fundamental point of view, it's like the experimental setup will be the same actually. So in one regime, you just get a imaging system, you just get a position correlation, just by imaging the center of the cell, and then basically in that you get 1 point correlated to its coherence area here. So in the other system, you get a Fourier transform of your center of the cell, and you just get momentum correlation or anti-correlation rather. So this photon will be correlated to the diametrically opposite regime of the other. And of course, data analysis and everything is the same as what we discussed earlier. So as a result, what we saw when we looked at the cross correlation measurement in the near field and far field, we got this result. And of course, the width of that tells me what is the uncertainty, or what is the fluctuation in my spatial domain actually. This will give me fluctuation in the position degree of freedom, and the width of this will give me this is the far field measurement. This will give me fluctuation in the momentum degrees of freedom. Of course, I did a 2D Gaussian fitting, and after that I got the width of this, and then finally what we got this result that again shows the EPR kind of situation. So that thus we conclude that we can show the EPR paradox with those bright beams. Moreover, earlier I was motivating in mid of my talk that in the previous experiment, what has been done with the FPDC, people had to take like tens of the thousands of images. But in our particular experiment, we did this analysis with the different number of images. As you can see that we did like the images from, let's say, 5 to 200. And then for all image range, this was our like the place where you can say that you have, this was our separability criteria, and we have below than the EPR bound. So our beams were entangled, basically EPR entangled with at least, or with just a few number of images. With the 5 number, we could get statistically significant result actually. Moreover, we did little bit more measurement on those kind of setup. So instead of just looking at the spatial, like the correlation or spatial scale, we just look at the noise reduction also. Or on the other hand, we look at the spatial squeezing. Spatial squeezing is nothing but spatial noise reduction in the near field as well as far field. And here you can see that, our noise reduction, this was our short noise limit, and this was the noise reduction. And then once we have squeezing in the near field and far field, what we did, we used Duan criteria or DLCZ criteria to show that whether we can show or we can claim the position momentum entanglement or not. Of course, the DLCZ criteria is if the variance in let's say position degree of freedom and some of the variances of position of degree of freedom like this, if it is less than 2, that means your states are not separable actually. You have inseparability. And in our particular experiment, what it came out to be like a 1.67, which is far below than bound 2. So thus we confirm the the spatial entanglement in our experiment. Last, okay, this was just completeness of the previous work. But what recently we have been trying, we have been trying. Okay, we know that. Okay, we have shown that spatial quantum correlation exists in the macroscopic regime. You can characterize with the CCD. Now we want to address the question that can we control those spatial quantum correlations? Actually, that's the next thing we are trying to do. So what we are doing actually, so we are now what we are doing, we are just engineering actually. We are changing the pump profile. We are changing the pump profile and looking at the cross correlation between, basically quantum correlation between these twin beams. And as a result, just this is one result I'll show you. So as a result, what we saw that when we had we started with just a very simple experiment or some simple demo actually. So if we imprint a certain phase pattern to my pump beam, we imprinted this to my pump beam by spatial light modulator, and then when we looked at the twin beams, images of the twin beams, nothing was changed much. So beams were looking like a Gaussian beam. But when we did the cross correlation measurement between these two, that was, we have some beautiful pattern actually. We got some like a kind of the correlated regions were kind of structured actually. So our correlated region got structured. Moreover, we did some theory simulation, and then we found that it's just what we got is just a angular spectrum of pump beam or angular spectrum of pump profile. This was my pump profile, and if I take angular spectrum of this, it turns out to be this. And then that's how we could get, or that's what we could get actually. So now whatever the pattern you want, you just can create that pattern by just making that shape to your pump beam. Any shape you want, you just shape your beam by using a spatial light modulator, and then that shape you can give to your quantum correlated beam or your quantum correlation. So this can have a lot of significance for the quantum information processing, where you use like a different spatial mode to encode your information or to process your information. So to conclude actually, so what I discussed today actually, I discussed the spatial quantum correlation properties of twin photon pairs. Of course, I showed different experimental demonstration and applications. And then I said, the photon pair generated by SPDC process have some limitations. So these limitations, or some of these limitations, can be overcome by using bright twin beams for a mixing process in atomic vapor. And then later on, we have shown the direct measurement of the quantum correlations with EMCCD camera. And then we show the APR paradox in its original position momentum form with bright beams. And then, of course, we have shown the APR entanglement by violating DLCZ criteria. So with this, I would like to acknowledge the people with whom I have collaborated, or my co-authors. This is Alberto Marino, actually, who was leading the group at University of Oklahoma, and this was this was undergraduate student working with me, and this was a PhD student. Again, he has started working in those areas, and of course the funding. So thank you very much for listening to me. Thank you.
Yeah, sure. So floor is open to questions. You can ask through chat box, or you can unmute yourself and ask questions. There is a question in chat box. I will read for you, Ashok. Can position correlation and momentum correlation be measured at the same instance? That is the question. Yeah, one question. Yeah.
No, that we don't measure at the same instance. In fact, that's what I said. It should not be confused. It should not be confused that we are measuring at the same instant. We are not actually. So because you have only one beam. If you do one measurement, you do like either position or momentum, and then you are inferring. You are making measurement on one system and then inferring the position and momentum of the other system actually. But no, they cannot be measured at the same instant.
Okay.
So,
okay, Ashok. So next question is, sir, I have not come across beats phenomena in the case of light. Can we observe such phenomena with correlated photons?
Yes, we can observe those phenomena with the correlated photons. So anyway, if you go the setup that I discuss here, in this system. So if you look at these conjugate and probe beams, their frequency difference is 6 gigahertz actually. They are 6 gigahertz apart, and then if you just interfere or mix those, and then you have a fast photo detector, then you can see a beat at 6 gigahertz.
Okay, so there is a question. Somebody has raised hand, so you can unmute yourself, Sohan, and ask question.
Hello, sir. In the slide where you showed about the angular spectrum of the pump beam, can you please go back to that slide?
Yes, sorry. Yes, please.
Sir, about this, you said about this angular spectrum, you said that this is the pattern which would be there on the, which will be created on one of those pump. So can we use this for quantum imaging?
This is just, this was not meant for the quantum imaging actually. This was actually, if you want to make, this was meant like if you want to make a correlated region, for example, okay, first thing I should make it clear that, just hold on. So in this setup, actually in this, just I'm not able to, wait.
It's okay. You can explain on this.
So yeah, this was just, to engineer your spatial quantum correlated region actually. So what we are doing in this one, or first thing is why you are getting the angular spectrum actually. So the thing is what you are doing, your measurement system is at the Fourier domain actually. And what you get at the far field is like an angular spectrum of the pump photons or pump spatial distribution that is at the center of the cell. So this was meant for just to like engineer different kind of correlation, or just to get different kind of what I said, like the spatial modes in your beams actually. So it was not for the quantum imaging actually. So if you want to get the quantum images, one of the previous setup I showed to you actually, if you put some of the pattern to your input probe. If you put some pattern to your input probe, then your conjugate and probe can have the same pattern actually. Then in that you can use for the quantum imaging. What I hope is clear. What I was telling you here in the previous slide. Here. So what I was telling you, if you put a mask in the probe beam, that mask can provide you the quantum images like this actually. Your probe and conjugated can have the same images, same pattern. Yes.
Okay, so there are other questions. Somebody wants to ask question. I don't see any question in chat box. Anybody else? Hello.
Yeah, Ashok, I have a question.
Yes.
See, people talk about different kind of correlations, like Discord, coherence. So here, entanglement, of course, is another. So sort of, can you differentiate, between these different kind of quantum correlations?
So what what I mean, like when we talk about if I understand correctly, the correlation could be, or what correlation we are talking, or if you look at the individual beams, actually individual beams, they are noisy actually. But if you look at the correlation between these, or when we talk about the correlation, or whatever, or in all the degrees of freedom, whatever people talk about the correlation, they say that if, or it is like a general, as far as I know, actually, it's a general practice that if you can show your correlation beyond the standard quantum limit, that gives you quantumness to your correlations. So I'm not aware of anything that is like I'm not aware of anything that you are above the standard quantum limit and you are saying that they are correlated. So the benchmark is the standard quantum limit actually. If your correlations are beating that allowed by the standard quantum limit, then you say that you are in the quantum limit, or you have quantum.
So you're looking from the perspective of measurement.
Yeah,
maybe 1 by root n or 1 by n, those kind of.
Okay, yes, yeah, that is like a 1 by root n is SQL and 1 by n is Heisenberg limit, that's ultimate limit.
Okay. Yes. Now, did you achieve 1 by n?
Excuse me?
Could you achieve 1 by n?
No. We have not yet achieved. Actually, we have not. Actually, recently we are trying. Actually, a theory paper came out recently. We did some sensitivity measurement, but with the squeeze light. Actually, this is just a theory paper we worked with. Like, of course, in the previous group. So recently, it's like in this 2-3 weeks back. It is in archive. So where we have used this kind of squeezed beam, and it turns out that squeeze beam are very, very good to get close to the Heisenberg limit actually. Of course, there are like the best. If you call a theoretician, they will say that best is noon state. But noon states are pretty fragile actually. You cannot work with noon state actually. But if you compare all the things like losses and all the things you take into account, then squeeze state turned out to be robust against losses, and then it can reach to the Heisenberg limit faster than the other states.
I see, yes. Yeah.
So, Ashok, can you come to the last slide? Let others think about the questions. Angular spectrum thing. Yes. So this one. Yeah. This thing, if you have noticed, so this thing we observe in SPDC also. Down convert photons. Similar structures, like it is guided by the pump spatial mode. When you do the coincidence imaging, you get the similar mode. So it's similar. Another question I wanted to ask, since you are doing this continuous variable position, momentum, and entanglement study, suppose you have some different mode. Instead of Gaussian, suppose you put vertex mode or elliptical Gaussian or elliptical vertex, asymmetric vertex, and then you study this position momentum entanglement and see the DLCZ criteria, whether your value, like your violation from like value much lesser than 2 compared to Gaussian, or what will happen? Have you
actually the problem will be, so the problem with working with like the complicated structure is the matching actually. So what I was telling you here, the main problem that arises actually this particular thing. So when you want to look at the noise, then if you have a Gaussian profile, if you have if you have a 2 beams with the Gaussian profile, they are easy to match actually. You can mode match, and then basically to get the noise reduction, you have to overlap 2 beams and then reduce. Then what you do, you just subtract the beam. But if you have some complicated pattern actually, it's hard to get this kind of mode matching actually, or the matching between 2 profiles that lead to squeezing actually. So it gets really hard if you have like engineered or different kind of shapes actually. So that's you will not get the main thing is the coherence area that you get with the Gaussian is like a Gaussian. But if you're coherent and moreover, what you have to do when you are doing those kind of measurement, your spatial scale or your detection or the detection area that you are considering, it has to be larger than the coherence area, or you have to bin or you have to group 10 by 10 pixel and then do the noise analysis of the combined beam. Why it is so? Because one point is correlated to a big region, but suppose you are losing half of the region, that means you have lost half of the correlated region. So if and moreover, if you use a kind of different engineered beam, as you said, like Gaussian elliptical beam, then first what you have to do, you have to find what will be your coherence area, that is spatial scale that you have to put in your detection system actually, or you have to bin it. So because if you lose some part of it, of course your correlation is going to be die actually. So because one part is correlated to, it can be correlated to any of the region actually, it's a big region. Yeah, that is the main challenge while doing complicated structure.
Okay, but there are theoretical studies, if you use non-Gaussian non-Gaussian states, so you can increase the entanglement in this position momentum kind of thing.
I saw.
But those are theoretical only. So one should try experimentally. I think that's the idea.
So in fact,
it will be difficult. It will be challenging, but one can try.
That was the when I left here US. So that was the thing. I got it, and then after that we are trying like more complicated. This is the result that I got there, and then after that there was a complicated structure, and then more analysis we are doing actually, still going on.
So any other question to Ashok? What is the time?
Yeah, what is just one last question?
Yes.
Can you just tell a little bit more about that noise correlation, what you observe?
Yeah. So what I was telling you about the noise. Yeah. So the beauty of this is, if you look at these beams, they are just look at like a DC profile actually.
Right.
What we have always, we have mean plus noise, right?
Correct.
On top of DC, there's some fluctuations actually.
Correct.
So now how to get these fluctuations on the beam? So for that, we have to subtract out those DC component actually. Because DC doesn't fluctuate actually. If the mean doesn't fluctuate. Mean is mean actually. So to subtract those DC or the mean, so just we basically subtract images captured in fast succession actually, in a rapid succession, and then we look at that's how we got the fluctuation in either of the beam. The fluctuation basically, they are intensity fluctuation. They are the intensity fluctuation over my image, and other also is intensity fluctuation over the image. Now the point is what I'm interested. I'm interested in the correlation between these two intensity fluctuations. Now you can do cross correlation analysis, or you can do differential measurement, whatever you would like to do, that we can do. But the main thing is, the main task is to get a spatial fluctuation, because when we talk about the spatial correlation, you have to look at, okay, spatial correlation in what? Spatial correlation in the fluctuation, intensity fluctuation.
Okay.
Yeah.
Okay. Yeah. Thank you.
Yeah.
Okay. So if there are no more questions, let's thank Ashok. It was a really nice talk.
Thank you.
And lot of applications it may lead to, very up to this quantum science and technology applications.
Yeah.
So thank you, Ashok.
Yeah, thank you. Thank you again for this opportunity, Professor Panigre. Thank you.
Thank you. Thank you. Welcome. Very nice.